Okay, so we're going to finish up some of the classwork from today. This is still another one from 7.1, doing the confidence intervals for a population proportion. Here we're doing one with cell phone use in cancer, not super uplifting. So here we have a study of 420,095 Danish cell phone users. That's my sample size. That's a lot of people, a huge sample size, certainly over 30, sufficient enough for us to use our theorem and our process and trust it. But I'm still not the entire population. And we found out that 0.0321%, so not just 0.0321, 0.0321% of all the cell phone users have developed cancer of the brain or nervous system. Prior to this study, they said that they did another study on just general cancer rates without connection to cell phone users or not, and found the rate in the general population to be 0.0340% for people who do not use a cell phone. So part of what we want to do is, first of all, in part A, come up with a 90% confidence interval for the percentage. Percentage is the same as proportion. So I'm given a percent, which is a proportion of people. So this is finding a confidence interval for a sample proportion of where the real percentage of people who use cell phones get cancer is. Do I think it's going to be 0.0321% plus or minus 0.04%? Plus or minus 0.001%. What's that margin of error that I'm going to add here so that I can be 90% confident that the real percentage of people using cell phones who get cancer is somewhere in that interval I come up with. So we are again going to use the calculator to come up with the interval, so we don't really need to compute that error because we find the whole interval in the calculator, and it's a proportion. Then once I have the interval, I can answer the second question, do I think, based on my confidence interval, that using a cell phone actually changes rates of cancer by comparing it to the cancer rate for non-cell phone users? So let's go ahead and start part A. So in part A, again, the first thing we're going to do is we realize that this is finding a confidence interval for a sample proportion, right? A percentage is a proportion. So I need to know X and N. Remember, P hat is the decimal that represents X over N. To use my calculator, I need X, the actual number of cell phone users out of the 420,095 that got cancer. So I'm going to have to set up an equation. Be careful. This is a very small number, but it's a percent. To change a percent to a decimal, I move the decimal back 2 places. So my P hat is 0.00, right, when I move it back 2 places, and then 0.0321. Right, I had 0.0321%, move the decimal back 2 places. This is my percent written as a decimal. That has to equal X, the number of cell phone users, divided by N, my total population, 420,095. So to find that number X, I just multiply both sides of the equation, right? The opposite of division is multiply. I'm going to multiply both sides of the equation by the 420,095. So I'm going to take my 0.000321 times 420,095. And that's going to give me 134.8. Your calculator is going to want a whole number for X, its actual number of people. So we'll round that up to 135. So X is about 135. So out of all 420,000 or so Danish cell phone users, 135 of them are the proportion that got cancer. Now I'm going to put that into my calculator for the confidence interval. So in this case, I'm going to go again, stats, test. This is a confidence interval for one proportion, so one proportion Z interval. Now my X, that's what we had to compute on our own. We figured out was 135. And the total number of people in my sample is 420,095. The confidence level that I'm looking for is 90%, so 0.90. And then I can hit calculate. So then my calculator, again, make sure you know how to read your calculator. The E stands for exponent times 10 to the negative 4th. That means I move the decimal back 4 places. So in this particular case, I should be getting an interval of 2.8 times 10 to the negative 4th and between 3.7, 10 to the negative fourth. So let's write that down. We got our interval, 2.8. That notation of e to the negative fourth means times 10 to the negative fourth, and between 3.7 times 10 to the negative fourth. And again, reviewing scientific notation, that's the same thing. I move the decimal 4 places to the left. So that would be 0.123028. And my upper bound would be moving it 4 places to the left. That should be, whoops, I don't know where I got 3 points. So moving that 4 places to the left is going to be 0.00037. So now putting that together in words, I would say that I am 90% confident that the percentage, let's put it back in the same form it was given to us, the percentage of cell phone users who get cancer, so I'm implying from the whole population, is between, so now if I want to put these in percents, I'm going to move this to the right twice. So 0.028% is going to be something less than the actual population percentage, which is less than, moving again my decimal 2 places to the right, 0.037%. So I'm 90% confident, based on my sample of 420,095 Danish cell phone users, that the real percentage of cell phone users who will get cancer will be somewhere between 0.028% and 0.037%. The second question here, so in part B, they're now saying, does that appear to have, do cell phones seem to have an impact on getting cancer? So let's draw a picture. So if I draw a picture here, here's my number line, and here's my interval. Here's, 0.028 right here. So 0.028, and then somewhere over here would be 0.037. So this is the interval that I am 90% confident is the real proportion of cell phone users who get cancer. And then the number they gave me of non-cell phone users is 0.034. Well, 0.034 would have to be somewhere right smack dab in the middle. So since the percentage of non-cell phone users who in fact get cancer is in the middle of my confidence interval, it doesn't seem that using a cell phone has any impact, right? The people that got, the percentage of people who got cancer who don't use a cell phone is most likely the same as the percentage of people who get cancer that do use a cell phone, with a 90% level of confidence. All right. And then the last one that we are going to do, and we'll do this quickly because we did actually do it in class, is number 20. So to review for something like number 20, and now they're asking us to find the mean. So how do we know the difference between what we just did? Is that it tells me. It says here, construct a 95% confidence interval for the mean time required. It's also not giving me a proportion. It's giving me a list of data. I am not going to find the mean the hard way. I'm going to put it into my calculator. We did do this one in class, so I'm just going to kind of write down the summary. You can go back and watch the video of today's lecture from the morning to see all the details when we walk through this problem. But I would go to Stats Edit and put all these numbers in my list. You'll see here I already have them all in my list from this morning. There's my, I had forgotten one, 4.5. So there's 20 numbers all entered in here. Then I go to Stats, Tests. Now this is a mean, and I do not know sigma, the population standard deviation. All I have is a sample test. So I'm going to do an interval, and because I do not know sigma, I'm doing a t-interval. I'm using a t-score to adjust everything and standardize everything. A t-score is where I count, where I use that estimation of the standard deviation because I don't know the real one. So this is a t-interval. I hit enter. It gives me the option to either put in the statistics. I'm just going to click that for a second so we see. That would be if I already know what the sample mean is and the sample standard deviation. I don't. I've got a list of raw data. So that's what it means by data. So I click data, and I'm going to tell the calculator what list I put that data in. And then the calculator will compute for me the sample mean and sample standard deviation of that data set. So I put everything in list 1. I'm going to keep my frequency as 1. I didn't make a frequency table. and then I tell it the confidence level I want. And in this case, I want a 0.95, 95% confidence interval. And then when I hit calculate, it will give me the confidence interval, and it will also summarize for me the sample statistics, the sample mean and the sample standard deviation. So in this case, they tell us that the sample mean is going to be, so kind of summing it up, right? I got from the calculator, oops, I'll put it down here below, that my sample mean X bar turned out to be 6.5. And then the sample standard deviation, the notation for that is S, is 3.51. And N is 20. I have 20 numbers here that they gave me to use. And then from the calculator, it gave me an interval where it said that the end was at about 4.86 and the upper bound was 8.14. That is none of the symbols I wanted. So putting that into words, I would say that I am 95, not 6, 95% confident that the mean years to earn a bachelor's, which I'll call BA, is going to be between 4.86 and 8.14, and the symbol I'm going to use here is mu, because I'm claiming this is where the real population mean, right? I was given a sample mean from one sample set. Based on that, I'm claiming that the mean for the entire population, which we use the symbol mu, is between 4.86 and 8.14 years, right? My units here are years. We're talking about years for getting a bachelor's degree. I'm 95% confident that that's the amount of years it's going to take on average given this data. The next thing that it's asking us is, does it appear that college students typically earn a bachelor's degree in 4 years? Not from our conclusions. However, is there anything about this data that suggests that the confidence interval maybe isn't a good result? Maybe we can't really trust this. And the answer is yes, this is not a good result because it doesn't fit our criteria, right? We don't know if the regular population is normal. So the population may not be normal. And the sample set is less than 30. Remember, in order for this process, the process that our calculator is going through, the computing of error in this way is based on either a normal distribution of the original data or sample sets of more than 30. This sample set is only 20. That is not more than 30. And it did not tell me that the data was normally distributed. And in fact, we can kind of eyeball this. If I were to graph this in a histogram, right, draw like a line chart here, a bar graph, that it would definitely not be normal, right? Here would be 4, here would be 4.5. They'd be the same height, and then 6, and then 8, and then 9, and 13, and then 15, right? So it's not anywhere near normal, and it's less than 30. So building the confidence interval in this way is not going to be really reliable. All right, so good luck finishing the rest of 7.1 and 7.2 homework, and we will be Zooming again tomorrow on Tuesday morning.